We'll now start the topic of static longitudinal stability. The information can be found in the textbook in Chapter 20 and 21. If you remember from the first lecture of Chapter 19, we defined stability, and static stability was the initial tendency to return to trim after being displaced or disturbed. In the illustration here, the airplane's flying straight and level, and then it gets a pitch down disturbance. So we want to look at what's the initial tendency after the disturbance. We can see that the purple behavior shows the airplane trying to get back to level flight, so its initial tendency is to get back to trim. The light blue line shows that the airplane after the disturbance just wants to continue down that straight track, so that's statically neutral. And then we see the pink line that after the disturbance, the nose of the airplane wants to continue to go down further, which means it's statically unstable. So now we'll distinguish between just static stability and longitudinal static stability. When you're flying in an airplane, the longitudinal motion is pretty much when you push forward on the stick, pull aft on the stick. It's motion about the lateral axis, the YB axis. And the motion is in the plane of symmetry of the aircraft, the X body, Z body plane of symmetry. So this is a confusing point. It's longitudinal motion, but it's motion about the lateral axis, the Y body axis out the right wing. Now the good thing about longitudinal motion is it doesn't couple with the lateral directional motion, which simplifies its analysis. The types of maneuvers that we want to look at longitudinal static stability are really maneuvers that don't really maneuver at all, or non-maneuvering tasks. Things like takeoff, climb, cruise. These are fairly steady things that we do. We're not rolling the aircraft. We're not yawing the aircraft. We're just raising the nose a little bit, pushing the nose down a little bit. So takeoff, climb, cruise, gliding, descents, approach. These are all longitudinal static stability maneuvers. To fly an aircraft safely, we need to be able to balance or trim the aircraft. The aircraft needs to have positive static stability, and then we have to be able to control the aircraft. Stability is assessed from an equilibrium condition, in other words, a trimmed flight condition. And mathematically, the airplane is trimmed or balanced when the sum of the external forces is 0 and the sum of the external moments are 0. And so we look at the airplane in the diagram and we see all these forces, and some of the forces go forward, some go back, some go up, some go down. But the sum of the forces have to cancel out and basically go to 0, and then the moments generated have to also sum to 0. Static stability, again, we're concerned with the initial rotational motion tendency of the aircraft after it's disturbed from a trimmed flight condition. Pilots think a trim means I can take my hands off the controls. The airplane is balanced. Now, let's look at longitudinal trim. So here's an aircraft flying straight and level. It has a center of gravity called CG, and that's where the weight vector acts. The main wing generates lift. You can see this CL, that's the coefficient of lift generated by the main wing. And then you see a downward vector of the tail lift. So when we sum the moments about the CG, we look at the forces by the main wing and the force by the tail, and they have to balance. So the main wing generates upward lift, and it's at a short distance from the CG. And the tail needs to counter that with a downward lift, and it's at a longer distance from the CG. So the tail doesn't need as much lift because it's at a longer distance, but it still needs to counter or balance the lift from the main wing. In the introductory lesson in Chapter 19, we talked about the equations of motion. We derived those from Newton's law, and we derived 6 equations of motion. We rearranged them, and we came up with 3 longitudinal equations of motion, and they're listed here. Let's just go over again what these are made up of. The left-hand side are the external forces and moments that are generated on the aircraft. The right-hand side is how the airplane responds. And we have all the different things we define: forward speed, side speed, downward speed. We have pitch rate, roll rate, yaw rate. We have moments of inertia, products of inertia, mass. All these parameters were defined in our opening lecture. And that's all the airplane response on the right-hand sides of the equations. Let's now focus on the left-hand sides. We have forward motion, and so there's going to be forces in the x direction. Up-down motion, forces in the z direction. And then rotational or pitching motion, which was denoted by the symbol m, and that's rotation about the y body axis. So that's up-down rotation, nose up, nose down rotation. When we analyze pitching motion, or the pitching moment m, we're going to use a calculus-based technique that has stability derivatives and control derivatives. So the stability derivatives, they measure how much change occurs in a force or a moment that acts on the airplane when there's a small change in a flight condition parameter such as angle of attack, airspeed, altitude, etc. Control derivatives, on the other hand, they measure how much change occurs in a force or moment acting on the vehicle when there's a small change in the deflection of an actual control surface, such as the aileron, the elevator, or the rudder. In the case of pitch motion or pitch moments, the elevator is what's going to generate the moment, delta E. So the calculus-based model uses these stability and control derivatives, and it breaks down the moment on the left-hand side of the equation into these sub-elements. So there's a moment with 0 angle of attack, that's m sub o, and then there's the moment of speed, and then there's the moment of alpha, angle of attack, then there's the moment due to pitch rate, etc. So this is the calculus-based model of using stability derivatives and control derivatives. All of this builds to that 1m on the left-hand side of the equation on the previous slide. Now all these partial derivatives, partial m, partial u, partial m, partial alpha, etc., makes the notation somewhat cumbersome. So to simplify the notation, they replace the partial derivatives with this subscript notation. So instead of saying partial m, partial u, it's just m sub u. Likewise, partial m, partial alpha is m sub alpha. So this is a way to analyze pitching moment or aircraft motion using a calculus-based technique called stability derivatives and control derivatives. To make the model on the previous slide less dependent on units, they've developed coefficients that are non-dimensionalized. And so instead of moment, we're going to have the coefficient of moment, c sub m. And you can see it's the pitching moment m, and then we divide it by some parameters that make it non-dimensional. And in this case, it's 1/2 rho, which is density, v true, which is true airspeed squared, capital S, which is the wing area, and a term called c bar, which is the length of the mean aerodynamic chord. So the stability derivative m sub u then now in coefficient form becomes c sub m sub u, and it still has mu, and then it's non-dimensionalized by the same denominator, and it also has a moment of inertia and a true airspeed in the numerator. So this is an established practice that aerodynamicists have done to basically take the model on the previous slide and make it non-dimensional using these coefficients as we've defined here. So one other thing you'll see sometimes is instead of writing 1/2 rho V true squared, they'll just use dynamic pressure. Q bar is the same thing as 1/2 rho V true squared. So sometimes you'll see the coefficients listed with Q bar instead of 1/2 rho V squared. But when you do this, the equation on the previous slide then has a coefficient form at the bottom of the page. So the moment coefficient is Cm0 plus Cmu times U plus Cm alpha times alpha, etc. It's the same type of equation, it's just now we have non-dimensional coefficients. We already said that the pitching moment m really has a function of a lot of things: forward speed, angle of attack, pitch rate, etc. But for static stability, we're going to limit the analysis of pitching moment to really the impacts of angle of attack and elevator alone. We're going to ignore forward speed and pitch rate, etc. And for static stability, it's just the pitching moment due to angle of attack and elevator deflection. So we can take the equation on the previous slide and just simplify it, drop the terms that don't matter, the CMUU and the CMQQ, and we're down to now 3 terms on the right-hand side. Now when we trim the aircraft, hands off, it's going to be a certain angle of attack and a certain elevator that got us to the trim condition. But in trimmed flight, the pitching moment is 0, and the coefficient for pitching moment, Cm, is also going to be 0. Now we're trimmed, and we want to analyze the motion of the aircraft due to a disturbance or a change in some variable. So the bottom equation is a change in pitching moment due to a change in angle of attack or a change in elevator deflection. When we look at the pitching moment, there's 2 cases: stick free and stick fixed. We're going to start with the stick fixed case. So the control positions are held in a fixed position. They're constant. The elevator deflection is constant in this case. For lack of a better value, let's just assume it's 0. 0 is a constant number. It won't change the analysis, but right now it'll make understanding the concept a little simpler if we make the elevator 0. It drops that 3rd term. What we get then is the classical high school algebra y equals mx plus b type of relationship, a linear plot. So there's going to be a slope and there's going to be a y-intercept. In this case, the y-intercept is Cm sub 0. It's the pitching moment coefficient when the angle of attack is 0, but it's really the y-intercept. And then we have Cm alpha times alpha. The Cm alpha portion is the slope of the line, the change of y over the change of x. On the graph shown on the right, you can see that that slope is negative. So we have a positive y-intercept, a negative slope, and then the line eventually intersects the x-axis. When it intersects the x-axis, the overall pitching moment, the y-axis, value now is 0, which means the airplane is trim. There is no pitching moment. And so that angle of attack, which is the x-axis, that got us to that point is the trim point, or it's the trim angle of attack, alpha sub e. Longitudinal static stability is concerned with the initial pitching moment response, that delta pitching moment, when there's a disturbance in angle of attack, or delta alpha. A statically stable aircraft will generate a restoring pitch moment opposite the angle of attack disturbance. What do I mean by this? So if I have an angle of attack of, say, 6 degrees, and then I get bumped to 8 degrees, well, we want the airplane to push the nose back down to go back to the trim angle of attack of 6. Likewise, if I'm trimmed at 6 degrees angle of attack and a gust pushes me to 2 degrees angle of attack, I want the nose to come up then, the natural restoring moment to come up to get back to 6 degrees angle of attack, if that was my trim value of angle of attack. So again, we want the restoring moment to be in the opposite direction of the disturbance. Another way to look at that is going back to the CM versus alpha curve, the linear relationship we showed earlier. Again, we said when that curve crosses the x-axis, that's the trim point. That's the angle of attack that was needed to trim the aircraft to have zero pitching moment. In this example, alpha E, if we get a disturbance in angle of attack that makes the overall angle of attack larger, so let's say, again, alpha E was 6 degrees. If we go larger, that means we're to the right of alpha E at something like 8 or 10. And if we look at the plot, it means that we need a negative pitching moment. We got to think of the right-hand rule in this case, right? The YB axis is going out the right wing. And so a negative pitching moment using the right-hand rule would push the nose down and get us back to 6 degrees angle of attack. Likewise, if I'm at 6 degrees angle of attack and I get pushed to a lower angle of attack like 4, that's equivalent of going left on the axis from our alpha E. That puts me at a positive pitching moment, which is going to push the nose back up and get back to 6 degrees angle of attack. So whether we look at it from pictures on nose up, nose down, or we look at it on the plot, it's still basically telling us that for positive static stability, that slope, CM alpha, has to be negative. When we trim an aircraft in level flight, the overall lift of the aircraft has to balance the overall weight of the aircraft. Otherwise, we would climb or descend. So lift equals weight if we trim in level flight. Now this starts to cause confusion in the notation. Earlier, we defined L as a moment, and we defined W as a speed. In this case, L is now lift, not a moment, and W is now weight, not a speed. This is confusing, but unfortunately we're stuck with these variables in this nomenclature, and they do use certain letters multiple times, and we're forced to rely on the context of the problem or the equation to understand which letter means what. Let's now look at a typical lift curve. This is one of the basic curves that any aerodynamic book starts with. It's a coefficient of lift, CL is the y-axis, and alpha, or angle of attack, is the x-axis. And a typical lift curve is shown on the lower left portion of the slide. Again, CL is defined as L, in this case lift, divided by 1/2 the density times the true airspeed squared times the wing area. That's a classic definition of what CL is, the coefficient of lift. We see then, for an aircraft to be trimmed in level flight, it needs to have a positive angle of attack. So based on this linear relationship of CM versus alpha model, the trim then for a statically stable aircraft is also going to require that that y-intercept at CM0 also be positive. On the plot on the lower right of the screen, you see two CM versus alpha lines. The top one has a positive CM sub 0, or positive y-intercept, and we're able to cross the x-axis at a positive angle of attack. The lower curve has the same exact slope, but its y-intercept is negative, and we cross the x-axis at a negative angle of attack, and that's not possible based on the CL versus alpha relationship and the CM versus alpha model. So again, we want a positive CM sub 0, or positive y-intercept, and we need a negative slope for static stability. So in flight test, angle of attack is sometimes not available or hard to measure, and so we may want to look at our analysis based on something we can measure, which CL is actually something we can measure quite easily in flight. So I can take the relationship for static stability, the fact that CM alpha needs to be negative, and I can derive an equation or another relationship that gives me another slope that I can measure in flight. And so here's the analysis. We have a definition for CM alpha, and then basically we multiply the numerator and denominator by partial CL, and we get a new mathematical definition now that CM alpha is nothing more than dCm divided by dCl times CL alpha, or the lift, the CL versus alpha slope. And we know that's positive from the previous slide. the bottom line is we need CM alpha to be negative, and in this problem that also implies that DCM over DCL must also be negative. And again, we do this because we can measure CL easily in flight. It's more accurate than angle of attack, and sometimes we just don't have angle of attack. So how do we measure CL in flight? Well, for general aviation aircraft, we fly at low Mach numbers, and so we can assume that our equivalent airspeed and our calibrated airspeed are essentially equal. That being said, I also have an equation now that relates equivalent airspeed to true airspeed, and that's the equation shown there. The true airspeed is the equivalent airspeed divided by the square root of the density ratios, rho sub 0 being the sea level density, and that's a constant value, 0.0023769 slugs per foot cubed. Density is whatever the density is at altitude. So since equivalent airspeed and calibrated airspeed are about the same at low flying general aviation aircraft, we can replace true airspeed with calibrated airspeed times the square root of the density ratio. Now if I substitute that in our lift equation, and since I'm in level flight, I know that lift equals weight, and I always know my aircraft weight based on the fuel burn and our empty weight and our weight and balance at the beginning of the flight. I know the weight. Then all the way to the right hand side of the equation, I know weight, sea level density is a constant value. I know my calibrated airspeed, and wing area doesn't change, so I'm easily able to calculate CL based on my weight and my calibrated airspeed. The other numbers are constants. So we said that CM alpha, or that slope, has to be negative for stability. And we can look at it now in terms of the degree of stability. So obviously the more negative the slope, the more stable the aircraft. So number 1 on the plot shows you the most stable aircraft. A more stable aircraft generates a larger restoring moment when its angle of attack is disturbed. So everything else being equal, a more stable aircraft is more resistant to disturbances. Now we have some other slopes shown on that plot to the right. We have slightly less negative slope in the number 2 curve. We have a 0 slope in the number 3 curve. And then we have a positive slope in the number 4 curve. So the number 4 curve is statically unstable. The number 3 curve is neutrally stable. And 2 and 1 are stable curves, where 1's being more stable than the second. So when we're looking at total aircraft pitching moment, or the left-hand side of the equation, we can kind of look at the sum of the individual aircraft components. In other words, the aircraft has a wing component, a fuselage component, propulsion components, and the tail component. So we can break them down one by one. And yes, this is an exact model, but it's actually useful for the understanding of the system. So we see in the graph on the lower right is you can see the different subsystems broken out. The wing alone has a positive slope. That's destabilizing. The fuselage alone has a positive slope. That's destabilizing. And so the main contributor to overall aircraft stability looks to be that tail. The tail alone is what gives us that strong negative slope that overcomes the other positive slopes. So other systems like propulsion systems, where the propellers and the jet intakes, etc., sometimes they're stabilizing, sometimes they're destabilizing, and even sometimes the main wing can be stabilizing or destabilizing. We'll talk about those here in the next couple slides. The main wing. The main wing generates lift at the aerodynamic center. At 0 angle of attack, it can also generate that initial pitching moment, Cm sub 0. And the aircraft will have a center of gravity based on where the baggage and the passengers and the other equipment are. The center of gravity moves. It can move as much as 10% of the mean aerodynamic chord to 40% of the mean aerodynamic chord. The lift of the main wing, however, typically acts at 25% of the mean aerodynamic chord, as shown in the diagram. But again, CG can move based on fuel burn, based on baggage, based on passengers. And so sometimes the main wing contribution has a stabilizing effect, no effect, or neutralizing effect, or a destabilizing effect. Next, let's look at the different propulsion systems and how they contribute to stability. In the upper left-hand corner, we see a propeller airplane, and generally the way that propeller works is it turns the airflow and it generates this NP, this normal force. And if you look at where the CG is, say under the pilot's window or at 25% of the mean aerodynamic chord, using the right-hand rule, that NP then would generate an upward pitching moment. So if you got a disturbance in angle of attack, it's actually destabilizing. It's going to want to continue the nose to go up. Likewise, for the jet in the lower left-hand corner, the same thing is that as the air hits the inlet, it generates that normal force of the inlet, which, based on the center of gravity and the right-hand rule, would give us an upward pitching moment or a nose up, and so that would be destabilizing. In the two figures on the right, you'll see that when the propeller is in the aft or rear section, or the engines are mounted on the aft or the rear section, it's actually a stabilizing effect using, again, the right-hand rule. So we talked about the main wing components, we talked about the propulsion components, and in the end it comes down to the tail. The tail is the largest contribution to static stability or stability in general. And the way you can look at the tail and the effectiveness of the tail is by a thing called the tail volume coefficient, which we define here as V sub h bar. It's made up of some ratios and a term called eta sub t, and we'll go through these one by one. So S sub t is the horizontal tail area, and it's shown in the diagram here. You divide that by the overall wing area. The wing area is always going to be larger than the tail area, so we expect that fraction to be less than 1. On the other hand, the next ratio is L sub t, which is the distance from the wing aerodynamic center to the tail aerodynamic center. That's a little bit of a large number relative to the mean aerodynamic chord, which is a shorter number. So that ratio is going to be greater than 1. And then eta sub t is kind of a tail efficiency factor, and if it's a conventional aircraft like the picture shown, we can assume it to be 0.9. But if we have a T-tail where the horizontal tail is in the smooth air, it's not impacted by downwash or other things or propeller effects. So if it's a T-tail, then we can assume that eta sub t is 1. But for a conventional aircraft, 0.9 is a pretty good ballpark. So again, on the lower right-hand plot, we see that tail is the main stabilizing factor that causes the overall aircraft Cm versus alpha or Cm versus Cl curve to have that negative slope we need for positive static stability. So let's analyze this graph again, Cm versus Cl, and we have the slope dCm, dCl, and it has different components. And so the question is, how do we change the slope? Or what impacts the change of the slope? And there's an equation here shows that we have a wing contribution, which is the location of the aerodynamic center compared to the CG. We have some propulsion effects. We have the lift curve slope of the horizontal tail, ratio to the lift curve slope of the main wing. We have that horizontal tail volume coefficient, and then we have this d epsilon d alpha, which is a change in downwash with angle of attack change. So a lot of different things are going into what's impacting the actual value of the slope. But if we really look close, all of the above terms are fixed except for that first wing term, that x sub a over c bar. And so we can vary that by moving the CG. Again, for positive static stability, we need the overall value of that equation, dCm, dCl, to be negative. And we're focusing on the wing contribution. So we said we can move the CG in the direction a number of ways. We can move baggage, we can move weights, we can move fuel, etc. We can move the CG. But if we move the CG in a direction that makes the wing contribution become larger, which is effectively moving the CG aft, we will eventually reach a point where DCM, DCL will actually be zero. That slope of that curve will be zero. And this CG location, when we move that CG aft back enough to where we get to that point where the slope is zero, has a special name, and we call that the stick fixed neutral point, given the symbol N sub 0. And what that really represents is the aerodynamic center for the entire airplane. And knowing the stick fixed neutral point, we can determine the slope of the curve using the equation shown at the bottom. So DCM, DCL, that slope, is the current CG minus the stick fixed neutral point. And the difference of those two, the current CG and the stick fixed neutral point, is also given the definition called the static margin. So margin of stability. Next, we'll switch over to longitudinal control. We've balanced, we've statically stable, but we still need to be able to control the aircraft. So we can trim the airplane at zero pitching moment, but from the graph we see that only occurs at 1 CL. And that would not be a very useful airplane. Airplanes need to fly at different speeds and different CLs. So we have to look at a method of a way to vary the lift coefficient. Go back to the equation and we look at the different terms and we say, what can we change to move the trim point? We can change the wing pitching moment, the first term. We can change the CG location, or we could change the tail angle of attack. That shows up in the last term. The other things are, for the most part, fixed. The wing pitching moment is a function of camber and twist. And yes, we can deflect the flaps at the wing trailing edge, or we can deflect leading edge slats, and we can change the coefficient of moment at the aerodynamic center, but we prefer to use those devices for high lift, not aircraft control. On the other hand, if your aircraft is tailless, like the B-2, you have to do something with the main wing for control. You don't have a tail. So that in that case, they do have to use flaps and other devices on the main wing for aircraft control. But for your average aircraft, the tail, again, is going to be the most important part that we use to change our CL. The second method we talked about was moving the CG. And we can do that. We can transfer fuel or ballast in flight in real time, but that's not very practical unless you're a hang glider. If you're a hang glider, you can move your body weight, and that moves the CG and gives you a different coefficient of lift. But for a real aircraft, there's limits, and if we move the CG too far aft, we become unstable. And that, in the case of the B-1, that caused an accident early in its development program when the wings were swept from the forward configuration to the rear configuration. The CG moved too far aft, and they weren't able to move the fuel in time to balance it, and they had to eject. So again, the last and best method to change the CL is to fly at a different angle of attack on the tail. And we can do this easily by moving the entire tail, which is a stabilator, or by moving a hinge surface at the trailing edge of the horizontal tail, which is called an elevator. It all comes down to the horizontal tail. We either move the whole thing or we move the elevator. And both of these devices produce large moment changes without affecting the slope of the CM versus CL or the CM versus alpha curve. So we get the same stability, but now we get multiple CL positions that we can trim the aircraft, and that makes it a usable vehicle. So in flight tests, we cannot readily measure moments about the CG. However, we can measure some related values that give us the overall same information. If we plot elevator position versus CL for each of the trim points that we saw on the previous page, we can generate a plot like was shown here. We'll see that the slope of the delta E versus CL plot is going to change based on where the CG is. So the one with the most negative slope is one where the CG is the most forward. And as the slope gets shallower, then the CG is moving aft, and at one point the slope at the top is going to be 0, and that's our stick fixed neutral point. So when we take this data in flight, it generally has a linear relationship, and we're back to our y equals mx plus b type of relationship, where we have the y-intercept, the delta E at CL equals 0, and then we have the slope of the line, and then we have the x-axis value, which in this case is CL. So we can write equations for these curves, and we can measure the slopes. So Cm delta E is the control power coefficient. It's got alpha t, tau, and the tail volume coefficient. In this case, tau is a tail effectiveness factor, which is 1 for a stabulator and something less than 1 for an elevator. Now the y-intercept, the delta E where CL equals 0, is a constant. And although we can't get this in flight, the actual value, just knowing that it's a constant is going to help us when we fare our curves from different CGs. We're going to want them to all intersect and point to the same y-axis intercept. If we differentiate the previous equation with respect to CL, we get this equation. Now we have d delta E dCl on the left-hand side, dCm dCl on the right-hand side divided by C sub m delta E. This equation is called the elevator position stability equation, and we see that the only way the left and right hand side are 0 is when dCm dCl is 0. So, or the vice versa, d delta E dCl is 0. That's the only way they're both going to be 0. And now we have an equation and a way we can measure stuff in flight, because we can measure delta E, the elevator position, and the lift coefficient, which I described earlier. Knowing the weight and the calibrated airspeed, we can measure those parameters in flight and generate those plots. So let's look how we determine the stick fixed neutral point from flight test data. In the class, you're going to be divided into data groups, and you'll have 2 data groups or 3 data groups, and we'll have you guys fly at different CGs. We'll move ballast around, we'll move students around, but we'll get a more forward CG, and then we'll have a group fly a mid CG, and then if we have a third group, they'll fly an aft CG. So we're going to collect data of the elevator position and the lift coefficient at 2 or 3 CGs, depending on what data, how many data groups we have. Once we have that data, we're going to plot it like in the upper right hand plot. You'll see that the blue line is for a forward CG of 10% mean aerodynamic chord. The red line is slightly more aft at 20%. The green line is at 30% mean aerodynamic chord. So each of these curves or these plots are for different CGs or a different data group. Now, so you're going to have to share data amongst your group to generate all 3 of these plots on the same graph. Once you have these plots, then you're going to want to fare a curve or a line through it and then calculate or measure the slope of each line. So there's going to be a slope for the green line, a slope for the red line, and a slope for the blue line. Once you have these slopes, then you're going to actually plot the value of the slope on the bottom plot. That will be the y-axis, and the x-axis will change to your CG location in percent mean aerodynamic chord. So you'll see the slope for the blue line is the most negative, and on the plot on the bottom, it corresponds to 10% mean aerodynamic chord, and its y component is the most negative. The red triangle at 20% mean aerodynamic chord has a slightly shallower slope but still negative, and then the green circle at 30% mean aerodynamic chord has an even shallower, and so we're starting to see those slopes kind of march their way up to 0 slope. We don't want to actually go out and fly at 0 slope because that would be dangerous, but we can see the trend here, right? And if we extend the line on the bottom plot from the the blue square to the red triangle to the green circle and just continue that line to where it intersects the x-axis, that is going to be the point where d delta E dCl is 0, which means that's the neutral point. So for this example, we extend that line, it intersects the x-axis at about 0.42 or 0.43. So 43% of the mean aerodynamic chord is the neutral point. So up to now we've talked about stick fixed static longitudinal stability. Next we're going to move into stick free static longitudinal stability. Stick free stability can be described as the longitudinal stability the airplane has when the elevator is free to float with the relative wind. The only way, or the only aircraft that have stick free stability are the ones with reversible control systems. So if you remember back to our introductory lecture in chapter 19, we defined what a reversible versus irreversible control system is, and I've shown diagrams here to refresh your memory. The bottom line is reversible means that the stick and the elevator are connected, and if I push on the stick, the elevator moves, or if I push on the elevator, the stick moves. They're connected by cables and push rods. An irreversible system, like the one shown on the right, is going to use hydraulics, it's going to use electric motors, fly-by-wire, etc. And so I can move the stick, and yes, that will move the control surface. However, if I move the control surface, the stick does nothing. So that's an irreversible control system. And again, only aircraft with reversible control systems have stick-free stability. Because an irreversible control system, the elevator will never float. It's never free to float. Control surface float is a function of the moments generated about the elevator hinge line. And these hinge moments, they can come from several sources, and I've listed a few here. It can be the camber of the horizontal tail, if it has camber. It can be the angle of attack of the tail. It can be the control surface deflection. It can be elevator trim tabs, a number of things. And so we can write one of these coefficient style equations that sum up all the individual contributions and calculate an overall elevator hinge moment, like shown here. So when the elevator is in equilibrium, the total hinge moment is 0, and the floating tendency happens to be canceled perfectly by the restoring tendency. When the elevator is in equilibrium, we may find the float angle by the equation shown. If the elevator tends to float with the relative wind, then the static stability is reduced. The stick-free static longitudinal stability can be expressed by the equation shown here. Notice that the stick-free longitudinal static stability has the stick-fixed static longitudinal stability term plus another term, Cm delta E times d delta E float divided by dCl. Both of the terms on the right-hand side of the equation are normally negative, so this causes the stick-free static stability to be less than the stick-fixed static stability. Stick-free static stability is also affected by the CG location. If we start moving the CG aft, we're going to get to the point where DCM, CG, DCL, stick-free is 0, and this point is called the stick-free neutral point, n sub 0 prime. And just like stick-fixed stability, we can define a static margin that we'll call the stick-free static margin, which is our CG location minus the stick-free neutral point, n sub 0 prime. These stick-free equations do not provide us with variables that we can measure in flight test. However, if we plot the airplane pitching moment stick-free versus CL, we see that to change the lift coefficient, the pilot must move the control to provide additional pitching moment. If the pilot doesn't retrim the aircraft, then he or she is going to have to hold a control force, either push or pull, to keep the aircraft at the new CL. And the magnitude of the control force required can be analyzed with that equation shown. With the previous equation, we need to know the values of CH delta E and CM delta E in order to actually determine the actual stick-free stability. However, if we look at the equation, the only way to get dCm, dCg, dCl to be 0 is if the change in stick force with equivalent airspeed, or dFs dV sub E, is also 0. So we have an indication of stick-free stability through stick force stability. However, this is only valid if the control system does not incorporate some of these control-free gadgetry items like downsprings or bob weights. Although an irreversible control system does not allow the elevator to float because the hydraulics or the electronics won't let it, the pilot needs the control force sensation of stick-free stability. So the way this is done on an irreversible control system is through artificial feel systems. In other words, the flight control system adds force to the pilot so they can feel like it's a reversible control system. In the early times, they basically just took a constant K1, some multiple of the elevator deflection, and that was the force that was fed back to the pilot through the control stick. Later versions, they brought in airspeed or dynamic pressure so that the different forces happened at different airspeeds. But let's go back to the control force equation. dFs over dVe, and then the other stuff. We can see on the right-hand side that this equation is a function of not just stability, it also has the aircraft trim information in there, so it's a little tricky to work with. But if we divide stick force by dynamic pressure, and then take the derivative of this quantity with a function as a function of CL, we get the equation on the middle of the page. And so we see here that most of the parameters are constant, and so the only way to get dm, cg, dcl to be 0 is if, on the left-hand side, d stick force divided by dynamic pressure divided by dCl is 0. Now we have something that we can, an equation that we can get variables that we measure in flight. We can measure stick force, we can measure dynamic pressure, and we can measure CL. So determining the stick-free neutral point from flight test data, again, we'll break up the class into two or three different data groups, and we'll have you guys fly at different CGs. One forward, one mid, one aft. And you'll record stick force data when the aircraft is trim, say in this case 90 knots, then you'll go lower speeds to 80 knots and to 70 knots without retrimming, and you'll have a force. Then you'll go above the trim speed to say 100 and 110 knots. And again, the pilot will record the force. Sometimes it'll be a pull force, sometimes it'll be a push force, but the raw data you'll collect in flight after you do the trim is the stick force on either side of the trim, plus or minus 10, plus or minus 20 knots on either side of the trim airspeed. Knowing the stick forces and knowing the speeds, the calibrated airspeeds, and the weight, you'll be able to calculate data now that has our lift coefficient on the x-axis and then our stick force divided by dynamic pressure, Q, on the y-axis, and generate three of these curves for the different CGs. From the previous curve, you'll be able to take the slopes, or d stick force over Q dCl, and you'll know the CG locations that those were done at. When you have that data, you can make this plot. With this plot, you can then extrapolate that data to where it intersects the x-axis. That intersection is when d stick force over Q dCl equals 0, or the stick-free neutral point. And you'll get, sometimes from the flight data, you'll get multiple neutral points, and that's okay. You can use the worst case one. but you'll have stick-free neutral points when you extrapolate that data to the x-axis. So let's bring all the points of static margin and static stability and stick-free, stick-fixed, all those things together, and let's just look at the wing section. Here's the main wing section. We know that the lift vector acts at the wing aerodynamic center, which is typically 25% of the mean aerodynamic chord. The CG right here is shown in a forward location, but that can move anywhere from 10% to 40% of the mean aerodynamic chord based on fuel burn, based on passengers, based on luggage. So that's a movable item. The aerodynamic center, though, the lift doesn't move. And so then we calculated different neutral points. We measured those from flight test data, and we have either a stick-free neutral point or a stick-fixed neutral point. And then the distance between the CG and either of those two neutral points is called a static margin. And we see here for an aircraft that doesn't have a gear tab or any other gimmick kind of devices, that typically the stick-free static margin will be less than the stick-fixed static margin. And again, the neutral points, whether it's stick-free or stick-fixed, really is coincident with the airplane, the overall airplane aerodynamic center. Again, the wing has an aerodynamic center, but the wing plus fuselage plus tail is going to produce an overall airplane aerodynamic center, and those coincide with the neutral points. So center of gravity positions can be summarized like this. If the CG is too far aft, the airplane will have insufficient stability. It'll be unstable. If the CG is too far forward, the airplane will have insufficient control power. So we have to trade off the control and stability, and we use the CG location as our envelope. In summary, longitudinal stability versus control is shown here. Again, the forward CG limit means I cannot trim the aircraft. The aft CG limit means I'm statically unstable. So our CG then needs to reside in between these two boundaries for the airplane to be both statically stable and trimmable.